for any object X we have to prove that at least some object is an element of the set. We suppose its negation, that is, no object is an element of the set. Object X we have, X does not belong to A. Okay, so this is my supposition. From this supposition, I have to prove that I arrive at a contradiction. Okay, now the statements X does not belong to A and X does not belong to the empty set are logically equivalent. Why? That's because by the definition of the empty set, I already have this. This is true for every object X. But according to my supposition now, also that similar thing is true for A. In A also, no object is an element. So these two things are always true. What that means what? Or in other words, X does not belong to A is true if and only if X does not belong to the empty set. Now this is a double implication. Okay, it consists of two implications. This one and this one. You know from our discussion of mathematical logic that an implication is logically equivalent to its contrapositive, right? So what is the contrapositive of this implication? Let me expand this place by removing the barrier. This is equivalent to the contrapositive of this implication. P implies Q. Negation of Q implies negation of P. That is, negation of X does not belong to the empty set implies negation of X does not belong to A. These two things are logically equivalent, right? But we can write it in a slightly different manner. Negation of X does not belong to phi means X belongs to the empty set. Implies negation of X does not belong to A means X belongs to A. So instead of saying this, we can also say this. They mean exactly the same thing logically. Similarly, if we run a similar argument here, we will get that this statement is logically equivalent to this statement. X belongs to A implies X belongs to the empty set. Okay? Now, what do these two things tell me? Every element of the empty set is also an element of A, and every element of A is also an element of the empty set. So that means by the definition of equality, I have A is equal to the empty set. Now this is my contradiction. Why? Because it is given that A is non-empty. So what you should understand what non-empty means. Non-empty means not being equal to the empty set by definition of non-emptiness. that has allowed me to conclude that there must be at least one object which is an element of A. Although that is obvious in our brain, but there is an argument behind that. Okay, it's once you follow the argument, it's not so obvious. Okay, so this is a contradiction, which is a contradiction, and hence our supposition is wrong. That is, we must have at least one object X which belongs to A. So there the proof ends. Now, what does this lemma tell us? Why is it called single choice? It tells me that if I have a non-empty set A, then from that non-empty set I can choose an element. That's what this result tells me. Okay, so that's why it's called single choice. From one non-empty set I can choose one element. Now, regarding that, there is a remark. So this is remark 3117. I don't know what is happening with the ink here. It is behaving like a ghost. Sometimes it comes, sometimes it does not. Okay, so the remark is just this. The above lemma asserts that given any non-empty set A, so just what I have said right now, we are allowed to choose one element X from A, which demonstrates its non-emptiness. Later on, in lemma 3512, we will show that if we have any finite number of non-empty sets, okay, suppose we have any number of non-empty sets where this n can be 1 or it can be 100 also, any natural number, n can be any natural number, all of them are non-empty. Then from each one of them we can choose one element. This also can be proved from the axioms that we write here. Okay, so and that result is said to be, will have the name finite choice naturally. However, if you have a collection of non-empty sets which is infinite, then you cannot use these axioms that we are going to write, all the axioms, to prove that from each one of them we can choose one element if this collection of sets is non-empty. Here the collection of sets is, the collection of sets is infinite. Here the collection of sets is finite. Here the collection of sets is a singleton collection. Okay. And this is where we need a new axiom that is called the axiom of choice. The general axiom of choice includes all the finite and infinite cases, but this cannot be obtained as a result of the other axioms. So this demands that we postulate something new, and that's why we need the axiom of choice.